Hello all. In this video, I am going to attempt the impossible. I'm going to try to give you a brief overview of multiple methods of machine learning that we are going to be using but not looking really closely at in class. These are kind of classic standard varieties of machine learning. They're particularly common in a number of AI applications, and they're useful, but we don't have time to really dig deeply into them. So I'm going to give you the high level overview. And then if there's something that might work for you for a project you're working on, hopefully you can then dig a little deeper and figure out how they work. And certainly in the activities and the assignments I'm giving you, I'm asking you to work with these models, even if we don't spend a class day or two learning exactly how they work. So this is like the inch deep intro to four or five different kinds of machine learning models. All right, so we're going to start here with k-nearest neighbor. And I will admit, I have a deep-seated fondness for k-nearest neighbor. It relates somewhat to the different, now somewhat arcane kind of machine learning I did in my graduate program. And I just love its simplicity. It also maps really nicely onto some things I learned about cognitive theories of categorization. It fits some cognitive theories quite well, and so it's just kind of fun and bizarre, and it's sort of an extreme end in terms of how it manages the task of machine learning. So k nearest neighbor. K is a variable, a parameter that we can specify. So we tell it how many neighbors, and then that's what it uses. So what is it doing? With k nearest neighbor, you treat the data set itself as the fundamental model. That said, we do allow ourselves to try to organize the data into useful data structures that make our search optimization better. But fundamentally, the model is the data. And we're going to categorize new examples not based on some abstractions from the data, but by using the actual data itself. So, what are we doing? When we are asked to classify a new example, the k-nearest neighbor model compares the new example to the ones that it had in its data set. And it finds the k most similar instances from the data set. So it basically is looking at similarity. We have to define what that means. And it finds the most similar examples it has, and it looks at how they were categorized. If they were all the same category, that's easy. Then you assign that category to your new example because it fits right in with all of them. If they differ, which is not uncommon, then what we do is to combine the recommended category from each of the k instances in some way. We merge them. We take the most frequently occurring. We look for the one that would win if they all voted. We exclude the outliers. There are just all kinds of ways you could do this. But fundamentally, we just take all of those different categories, and out of them, we decide on a category for the new instance. So there are some things that you have to deal with, parameters that you can change. You can change how you measure similarity. There are built-in standard measures that lots of people use, but you could have a problem where you want to define your own measure of similarity. What does it mean for two examples to be similar? Do you want it to weight all the attributes equally? Are there some that are more important? How do you want it to do the calculations? Do you want to use straight line distance or something else? Because we need to find the k most similar instances, we want to do that as efficiently as possible. That's what leads us to building data structures like KD trees, excuse me, in order to store the data set for efficient search. That's actually where k-nearest neighbor as something you implement becomes complicated and somewhat more interesting as if you like implementing hard things. You can build a brute force kind of k-nearest neighbor that just keeps a big array of all of the data set elements and it just linear searches through it. That will be slow, but it will work. So the data structures are to improve the speed of response so that you can work with larger data sets and still have a realistic chance of getting the answer you want. We also need to have some decision about how to combine the instance values somehow, which can depend on whether you're doing regression or categorization or something else. You could do weighted voting, you could do majority rules, you could do some kind of averaging of some sort if it's a more numerical response. It depends on the problem, and that's again something that you can choose. One of the nice things about k-nearest neighbor is that you can easily pivot from offline to online learning. So you could start with a relatively small data set and then have it build a starter model and then set it online. And as it has new experiences, you just automatically add those to the data set. And it's easy for the model to integrate new data. It might occasionally need to rebuild those data structures, but often they are extendable with a certain loss of efficiency. So it's a relatively easy approach if you want to do online learning. All right, that's it. That's all I'm going to say about k-nearest neighbor. One of the other really common machine learning methods out there is support vector machines. It's useful in certain areas. I will tell you that prior to the the existence of deep learning, support vector machines were really commonly used in computer vision applications because they tended to work really well. They work well with large, high-dimensional data, more so than some of the other algorithms that we've looked at. Explaining exactly how support vector machines work is complicated. It's pretty advanced mathematics. We're not going to talk about it. You can go and find resources that will go into all of that math, but just be forewarned that you need to have a pretty strong math background to really get everything that's going on. The ideas are not as hard as the actual math is. So what we are looking for with a support vector machine is to define a decision line, a decision hyperplane, and these supporting hyperplanes that divide the data. And it tends to think of things as a binary problem. The natural way of thinking of support vector machines is binary, a yes/no answer, not multi-categorization, but you can also do other things with it. It just complicates stuff. So we'll think about it in terms of a binary classification problem. We have positive examples, we have negative examples. We want to draw a hyperplane, draw in 2 dimensions like this picture. A hyperplane is a line. In 3 dimensions it's a plane. In higher dimensions it's a hyperplane. So we want to be able to draw a straight hyperplane through the data and split it between positive and negative examples. There are data sets where you can't draw a straight line through the attribute space. So even if we think of each attribute as a different dimension, so we have say 100 attributes, we're talking about a 100-dimensional space, there may not be a 100-dimensional hyperplane that can split the data because they could have complicated relationships. Well, there's a math that allows us to then project our data into more than 100 dimensions to get to a dimension where we can draw a hyperplane to split the data. Again, I'm not going to talk about how, but it's doable, and this is the sort of underlying idea. Now, let's just simplify things down. Let's just look at this diagram. I like this diagram. It's not too mathy, but it's got all the pieces in it. So let's assume that we have 2 attributes. X1 is an attribute, X2 is the other attribute, and therefore we can place all of our points just in this 2D plane. And in this case, we've chosen the data so that a hyperplane here, basically a straight line, can in fact divide the data. So if you look, I'm going to try to bring this up, and maybe it gets blurry and pixelated as I zoom in on it, so we'll have to do our best. If you look at this space, uh, hopefully you can see that there's a gap between the red examples and the blue examples. And we could draw a number of different lines that divide the data. So I could draw one that goes very, very close to this blue example and then down, and it works pretty well. I could have one that's closer to horizontal that just barely misses this red example and then barely misses the blue one on the other side. That also is a line that defines the data, or that divides the data. What a support vector machine is trying to find is it wants to find the line that maximizes the margin. So what is the margin? Well, we take points that are fairly close to the line, and we have these two hyperplanes, these two other hyperplanes that mark sort of a boundary for each case. And the center, the decision boundary, is centered between them. And we can again choose slightly different points in the space, and we could come up with slightly different sets of these decision line of the support lines and the decision line itself. So like if I left out this point right here, if I only had these two, I might be able to wiggle it around and find a different set of hyperplane lines that border, that you include the boundary of our data and the decision line itself. What we want to do is to maximize the distance between these two supporting hyperplane lines. We want it to be as large as possible so that the decision line is as far as possible from actual data points, with the idea that if we're too close to, say, the red point here, then the actual boundary might be out here in this no man's land between. There could be red examples that would fall on the wrong side of the line. That the best way to prevent examples from being on the wrong side of the line is to make sure our decision line is maximally distant from the examples on either side. And so it's called a support vector machine because we're identifying support vectors, support examples, that can allow us to define those two outer lines and define what the margin is and all of that. Okay, that's a whole lot, and it's a whole lot of hand waving on top of that. But that's the fundamental idea underlying support vector machines. You can see that they are designed to be extensible into multiple dimensions, which means they work well on larger collections of data, which is what makes them popular. All right, there are dozens of other algorithms, especially when you would start including regression in the mix. There's a whole family of algorithms for that. We're not going to focus on those. We're still sticking to classification. And what we're going to focus on next are ensemble learning methods, because these are fascinating. And some of the most popular machine learning algorithms out there are ensemble learning. And it's also just something that is sometimes people don't think to use ensemble learning when they might. So I want to make sure you understand what it's talking about. So what is ensemble learning all about? The ensemble learning says, well, if one classifier is good, maybe multiple classifiers would be even better. And so you have multiple classifiers, each makes a recommendation for the category that we are going to want, and then somehow we combine those results together and we get a final ultimate recommendation. There are two different kinds of ensemble learning collections. They're heterogeneous and homogenous. And they are homogeneous, however you prefer to pronounce it. They are really different. Homogeneous is probably more common these days because there are some standard algorithms that are that way. Heterogeneous, I think, is really interesting because it goes with this idea that maybe, say, a k-nearest neighbor system and a support vector machine are picking up on different regularities in the data. They're not just finding the same patterns, they're finding slightly different patterns, and they might strengthen each other. One might be strong where another is weak. So combining them, we might get a better result. So you could take a k-nearest neighbor system, you could combine it with a deep learning system, and you could add in another support vector machine. You've got 3 different trained models, and then you run them all on a new example and combine their results. I will note that IBM has their Watson system. Watson is fascinating. I have a video, very old now, from when they originally created Watson to play Jeopardy. And it goes all the way to the rounds of Jeopardy where they defeated the grand champions in Jeopardy with this Watson system. Watson, in fact, was an ensemble learning system. It had multiple different classifiers for different purposes and multiple classifiers that worked on the same data, and it took all of those different recommendations and combined them together to come up with its answers. I don't know how it works these days, but I would guess it could still have some of that built into it. There is an approach. You can, with heterogeneous systems, do something like voting or some sort of weighted combination of the recommendations from the different classifiers based maybe on how accurate they are or something like that. There is a specific approach that's called stacking, where you train these different classifiers on a data set and then you add their predictions to the data. So you take the output of each of those different models and you tack it on as additional attributes. So instead of just being, say, the good dog data set with its 4 attributes, you'd also have, and the KNN says that this dog is a yes, and the support vector machine says this dog is a no, and so on. And then you train one final classifier on that new data set. So you have a bunch of starter classifiers, and then there's another classifier that's looking at their output as well as the data and making its decision. So that's actually a fairly common approach. It's really kind of cool, and it gets you out of choosing what kind of voting or combination method you want it to have. When you have homogeneous ensemble learning, you have multiple classifiers of the same type, like a suite of support vector models. And they are all, again, working together, and somehow you're combining their recommendations. There are probably more than just 2, but there are 2 main methods that I want you to know about with homogeneous ensemble classifiers. One approach is called bagging, and the other is called boosting. Unfortunately, they both start with B, which makes it hard for me to remember which is which on the fly. But bagging and boosting are the 2. Bagging is a relatively simple approach. What you do is you make K copies of the same type of classifier, but you use slightly different versions of the data set. Here, I got to keep this where you can actually see all the text. So what you do is you take your original data set and you do random sampling with replacement from the data set, and you make a new data set and you train a classifier on it, and then you do a different random sampling and you train another classifier on it, and so forth. It feels a little cross-validation-y, right? Each one is getting a slightly different version of the problem. You look then to see how they've learned something different, and you combine the results with some sort of voting or other. This is the general idea of bagging. It's fairly simple. When you look at actual bagging algorithms, you often see that they tweak this process a little bit. And so the one that is really popular, I find, I just run across so many papers where they're applying random forest to problems. It's a very popular bagging method. You can use it without even really being aware that it's an ensemble learning system. So we're doing that in our activities using scikit-learn. It's just another kind of classifier. But it actually is different, and it's different in some really interesting ways. So what is random forest doing? Random forest is a bagging approach that builds decision trees. So the root idea would be you take a random selection from your original data set, you build a decision tree for that, you do the same thing again with a different random sample, you get a whole set of decision trees, and then you make a decision based on what they do. It's really nice because, again, this is explainable AI. You can look at those trees and see what is happening and why the decisions are being made the way they are. However, just doing that basic approach to bagging doesn't work very well, because when you build those trees, you find that they end up looking really similar. Because it's based on information gain, even if you resample the data set, the chances are that the gain is still going to be similar, and you'll end up building copies of the same tree that vary only slightly, and they're not really that helpful. They're not that variable. So there are ways that we handle this. One of the things we often do with random forest is we height limit the tree. So you build a tree, you say you can't have more than 3 questions, 3 layers, and then you got to bottom out at leaves. So you end up having to put leaves in even where you haven't absolutely completed the task. So that's one thing we do, is we height limit them. There's even one called random stump, where you're only allowed to ask 1 question in each subtree. But you still don't want it to have all of them choose the same question. The whole point is to have some variability. So we add additional randomness with the random forest algorithm in order to make it work better. So what do? It does, in fact, potentially reduce optimality, but then the forest nature of it gives you a bigger benefit than the downside of this. So at each point where we're building a tree, instead of looking at all attributes and picking the one with the highest gain, random forest only looks at a random subset of attributes. So of all the attributes you have available, it picks a random subset. It calculates the gain on those, and it picks the one that has the highest gain, but it's not looking at all attributes. So its set of attributes at any level of the tree is going to be different than what some other running of the decision tree builder is going to do. So it can be just as efficient as decision tree algorithms. Having this reduction in the number of attributes at each node actually makes it so much faster to compute gain and build the tree. It just makes especially if you imagine having, say, 1,000 attributes, having to search all 1,000 just to figure out which one is best, that's a lot of work. And so you can get a pretty good gain by having multiple smaller trees, each of which didn't look at all the attributes. And you hope that over the multiplicity of them, you'll cover whatever is important. It also is the case with random forest, because we're limiting these trees a bit, they don't overfit as badly. One of the problems with decision trees is that it's easy to have it build a bigger, more elaborate tree than it actually needs, where it's actually overfitting, it's learning features about the data set it's seeing that are not going to be predictive in general. So a lot of decision tree building algorithms have a stage of pruning the tree, where they try not to build some of the pieces that otherwise the algorithm would want to build. Because these random forest decision trees are smaller, they're either height limited or they're only looking at certain attributes, we have much less need to do that pruning, so the algorithm can be simpler. And you can build these trees in parallel. They run independently of each other. So you can actually parallelize this nicely, and that gives you a big boost in performance. So it can run as fast as a regular decision tree builder, even if you're building 10 or 20 trees at once. All right, so that's sort of a classic example of the bagging approach to homogeneous ensemble learning. The other approach, as I said before, is called boosting. Okay. Boosting has a sequence of classifiers that run in sequence. So instead of having separate classifiers, you build a first, and then a second, and then a third, and so forth. And the idea is that the first classifier takes a crack at the problem, and we can analyze on the training data how well it works and which examples it's not working so well on. And what we do is the next classifier that we build is designed to address the shortcomings of the first. And then we can add a third that knows how the previous two have done and where their weak points are, and it will then learn in such a way as to overcome the weaknesses of the previous ones. That's the fundamental idea of boosting. Each new classifier gives a boost to the overall performance because it's based on overcoming the weaknesses of the previous ones. So how do we represent those weaknesses? Well, what we do is to add to the data set weights. So instances are given weights, and those weights reflect how important it is that the classifier get that example right. Initially, all weights are set to be equal, 1 over n, where n is the number of examples in the data set. They're all equally important. And the first classifier works like that. And then when we've trained that first classifier, we can look at how well it performs, and we can identify the instances that it's not getting right. And we boost their weights. We say, these examples are not being classified correctly by the first classifier, so they're important for the second classifier to do. So the second classifier doesn't have something with even weights. It has some that are diminished in importance and some that are increased in importance. And that will change what it learns. And then again, we can keep adding them in sequence to each other so that they hopefully counterbalance one another and in the long run master all of the examples. All right, I'm doing this kind of in a hand-wavy way. There are lots more details. One of the classics of the boosting type of algorithm is eta boost. Eta boost strengthens the ones that this classifier got wrong and weakens the ones that it got right. That's sort of what I just described. Gradient boosting does something different. It looks at the gradient between what's right and what's wrong. So it thinks of the instances as being in a space, and it's got ones that the first classifier is getting right and ones it's getting wrong, and it can look at the gradient between those, and it uses that to change the weights to emphasize the parts that are more important in the space. There's also a special kind of classifier that comes up in computer vision called a cascade classifier. With a cascade classifier, how do we want to say it? It's kind of a special niche. It was used for face detection in the old days before deep learning existed, and it worked pretty well. So a cascade classifier, the first one would do the classification task. The second one was only allowed to look for objects in the location that the previous one had identified. So if you're looking at something like face detection, the first classifier would identify general regions that looked face-like. The next classifier would look only at those regions, and it would eliminate some and narrow some of the others, and then so forth and so on. So the only things that would be classified as faces had to make it through every single classifier in the sequence. And if the last one said, yes, that is a face, then we were pretty confident that it was a face. So that's another kind of boosting. It's a little bit of a special niche. All right, so again, once you have this sequence of classifiers, you take an instance and you run it through all the classifiers. Cascade was particular in that only the final result was used, but there's no reason you couldn't look at the results from all the classifiers. And again, use weighting based on how well each one works. You could use voting. You could use all these other different methods to combine the results together. This has been, as I said, a whirlwind coverage of a handful of other machine learning algorithms that we won't have time to look at really closely in class. So these are really cool. I encourage you to look at them more, keep them in the back of your head so that if you are doing a machine learning task, you have a set that you can start with. And then remember that there are literally hundreds of other machine learning algorithms or variations on the ones we've already studied that you could choose from. And choosing the right algorithm is a little bit of science. You look at the kind of data you have and what might be the best algorithm for that approach, but it's also a little bit of art. Maybe just try some and see which ones work best. All right, I'm going to stop there, and I will see you again very soon.